Yeah, good afternoon, everyone. Uh, I welcome all of you on a second day of 6 days STTP on practical approaches for data science in association with CSI and SSIP. So I hope yesterday you have enjoyed the session on introduction to fundamental of deep learning and gradient descent. Today, we are going to see how to read and understand the research paper by our eminent expert, Mr. Arjun Kawa sir, his CTO of Zuzo Technology. Sir has given detailed about yesterday's session, and it was really appreciable. And we have got very positive feedbacks from all the viewers. And today we are also hoping the same thing. So stay connected. And I'm handing over to Arjun sir. Please, sir.
Hello everyone. Thank you Narendra sir for your brief introduction. In the today's session, majorly we are going to discuss about the convolution neural network, and as sir said, we are going to discuss about how to read and basically try to implement the research paper. Okay, rather than wasting a time, let's get started. I'm presenting my screen, and let's start directly with the presentation. Okay, so basically, as we had discussed yesterday, at the end of the session, I had described that we are going to forwardly, we are going to understand about the convolution neural network first, and then we are going to understand how to read and try to implement the research paper basically. So, the goal of today's lecture is to first get the recap of what we had learned so far yesterday. Second thing, understanding the convolution neural network. And the third part is reading the research paper. Okay. Okay, let's first start with the recap portion, and we'll go through some of the slides we had learned about yesterday. First of all, we'll start with the basic perceptron. We had gone through the perceptron forward propagation yesterday, which is presented on the screen. There are multiple inputs, and then weights of their input, and then summation of weights and input product plus bias term is your output with the activation function of g, right? The next thing we had explored yesterday was a deep neural network, where we had staked multiple perceptrons and then get the output from it, as far as the and connected the whole perceptron to the multiple output nodes, right? Later on, we had learned about the objective function, or imperial loss, or you can say loss function, basically, where we had learned that how loss function differentiate the predicted and the actual outcome of the neural network. As described over here, we are taking the vector x, and the output is not matching with the actual output or actual result. So the loss function gives you the insight, or penalize the network and waits to understand that this particular outcome is not true. Then we had explored about the loss optimization using the argument mean, basically. The next part, we had explored gradient descent, and where we had basically gone through the multiple things regarding the initializing, how to initialize the weights, and then how to compute the gradient, and then how to update the weights via back propagation, and where we had learned about the chain rule basically, uh, which we can back propagate through the whole network and initialize or update the weights as per the actual, as per the difference of the actual and the predicted outcome. Then after we learn about the stochastic gradient descent, where we had explored like mini batch algorithm of the computing gradient, because for the huge data sets we are not able to compute this gradient in the only in the one competition, because of the limitation of the memory as well as the CPU. So practically we used to prefer mini batch system or mini batch gradient descent, where we are one step by step we are calculating the gradient of subsamples of the whole data set, and then we are achieving the updation of the weights, right? Okay, that was the so far recap we had learned so far, from the start of the perceptron to the and practical approach of the same thing. And yesterday we had learned, we had ran a simple algorithm which had classified the number from 0 to 9, right, using the MNIST dataset. In today's lecture, the major focus is on neural network, basically, and we are going to learn about. We are going to move from the perceptron to the actual convolution neural network. And in today's lecture, in the major case, we are going to explore the image data. So basically, the deep learning, the whole deep learning is also broadly classified into the multiple things, such as convolution neural networks, and then natural language processing, and then other neural networks as well. But the convolution neural network had been designed to actually deal with the vision data. Vision data is basically uh, images and the videos. So let's get started and understand that how convolution neural network basically works. Okay, the first thing we need to understand before starting is like, as we had seen in our perceptron model, that we had flattened down the whole two-dimensional space or multi-dimensional space into the one-dimensional space using the vector, and then we got the output. The same thing cannot be possible with the uh, convolution neural network, with the image data, basically, because the image data is high dimensional data. It's like it includes or it contains so many visual things and details, basically. So we cannot directly flatten out the image into the vector and then put as an input of the perceptron, because otherwise we'll lose most of the information, and it wouldn't be correlated with what we wanted to achieve, right? So uh, let's understand the basic architecture of convolution neural network first, right? As you can see on the in this diagram, there is a multiple stacks of some kind of blocks are there, right? I'll explain each and everything throughout this lecture. Let's first start it. Let's get the abstract overview of the each and every part of this figure. As you can see over there, there is the input and there is the output, and there are so many blocks in between, right? So let's take an example of as we had ran through the one program yesterday. You might have seen that that was the data set of numbers, right? 0 to 9. It was a MNIST data set, and the same image of that MNIST data set we had used over here, which is like 28 by 28 into 1. Now let's understand that first, the input part, basically. Over here, 28 into 1 does mean that the image of 28 by 28 pixel, right? And the third part is the channel of image. Channel means like usually we used to see the images into three channels, which is RGB, right? So we can see the colors. If you convert your channel into black and white or grayscale, basically, it only contains two major state, either black or white, right? So that is the third portion over there in the input, like 28 by 28 image having only black and white pixel data, right? So such kind of image we had given in the input of our neural network, right? And then as you can see over there, there is the first part called convolution 1, convolution of kernel and valid padding. Kernel and valid padding we are going to explore in the next slides. Right now it is something like the uh, what it does basically, it decompose or decompress or your high dimensional data into the lower dimensions. But it does mean that 28 by 28 into 7, which means like the data, your data is like kind of 784 dimensions if we plot it, right? So it is completely high dimensional data, and we cannot directly compute it or process it with our computers or get the features from it, right? uh, so what we are going to do with the convolution one is we are going to decompose the data into the into lower dimensions, like uh, and then the second layer, as you can see over there, in between the two convolution 1 and convolution 2, there are two convolution with using 5 by 5 kernel and valid kernel and padding, as I said, we are going to explain in the next lecture, or sorry, in the next slides. And one more thing, as you can see, in between two convolution there is a max pooling, right? The max pooling is basically a kind of uh, converting your uh, high dimensional data into the into stable version of that data. I'll explain more about the max pooling in the next slides as well. I'm just giving you the basic architecture overview over here. Then, as you can see, again, we had used max pooling in the last part of the network. And then we had flattened down the whole high dimensional data using fully connected network, right? Which is like FC, basically. This is the term we use in the deep learning, FC layer. So these are basically each and convolution 1, max pooling, convolution 2, max pooling 2, and FC3 and FC4 are the layers of your convolution neural network. And each layer have kind of their responsibility to process the data and provide it with the final output. Now this third FC3 fully connected layer, what it does, it flatten out your high dimensional data into the single vector, basically single one dimensional vector. And then fully connected 4, what it does, it actually map your one dimensional vector or kind of output dimension of your extracted image to the final output, or in a general way or in a simple way, it converts your high dimensional data into the probability, basically probability of the output, like is it a number 2 or not, had been decided at your fully connected layer 4, basically, right? And meanwhile, in between the fully connected 3 and fully connected 4, you can see the dropout function, right? Dropout function is basically a regularization. I'll describe it more in detail in the next slides as well. Okay, so far so clear. What we have right now in our bucket is convolution, max pooling, fully connected layer, and dropout, right? Okay, let's get started and let's understand it by each pieces. Okay, let's first start it with the uh, convolution operation, or basically the first part of the of our architecture, which is convolution layer, like convolution 2D. Why 2D? Because we are dealing with the image data, which is like in which is generally processed into the two dimensionals, right? If you are working with the video data, then you have to use the convolution 3D. But the same concept had been applied over there, but most of the things could be changed. Today, we are not going to talk about convolution 3D. We are just going to explore about the image data. Now, any of the image, basically, whatever image you are seeing over there, it is a collection of the pixel. Basically, it is a collection of the RGB, red, green, and blue pixels, right? And each pixel having their values, like between 0 to 255, as you had we used to study about the same thing, like converting image into the matrices, right? The same thing I had done over there. As you can see in the input image, the simple image which had been given into input had been converted into the tensor. Tensor is basically collection of your pixels, right? Like image pixel, like from, if it is 28 by 28 into 1, then it kind of 786 pixels are there. So what we'll do, we'll deal with the that 786 pixels. We'll convert the image into pixel values, and then we'll uh, give it as an input of the convolution layer. The same thing you are seeing over here, like in the input image. The image had been converted into the collection of pixels, right? RGB. 28 by 28 into 1. Size of the 28 number of rows, 28 number of columns. So you can easily distribute your pixels, right? Now, uh, in the second part of, or the in middle, you can see the future detector over there, which is like a simple matrix or a vector, basically, with 3 by 3 into 1 value, right? I'll describe it in detail, but right now it is kind of a future detector, or uh, the detector from which we can extract the uh, uh, features, basically, right, from our input image. And then in the last part, we had extracted the feature. So basically, the filters are uh, kind of image processing algorithms, right? If you dot product your input image pixels with this particular feature detector, then it will give you the image as described in the bottom of the slide, such as sharpen of image, blurring of image, or edge detect, right? So each and every image can be converted into the sharpen features and the blur features or edge detect using this feature detector. So as you can see over there, like in the input image, what we are doing is there is a sliding window over there. It's like 3 by 3 sliding window, where we are getting the values of that 3 by 3 vector, and doing the dot product with the feature detector, right? So the both of the dot product, the result is, you can see in the feature detector, the first 3 by 3 vector into the feature detector is equal to 6, and then second is 9, 8, 3, -2, -3, so on and so forth. So what it does, basically, it decomposes, or like it compresses your high dimensional image into the lower dimensions, right? Using multiple filters such as sharpening your image, blurring your image, detecting edge from image, or there are other filters as well. I have described 3 of them over here. So this feature detector, basically what it does, each and every convolution layer using feature detector, it basically uh, get the or compressed feature set from your high dimensional input image and convert into the feature map, right? using TensorFlow, as you can see in the top of the screen, you can basically do the same thing using tf.keras.layers.convolution2d, right? We'll explore the same code in the practical approach. Basically it does mean that you can directly use the convolution layer using this basic function, right? Okay, moving next. Uh, there is another two features with the convolution neural network as well, which is like kind of pending and stride, right? Now, the problem with the simple feature detector is like sometime it might be possible that the values which uh, at the corner of the image might be compressed into the many part. Basically the reason is like we are majorly focusing on the center of the image, but while doing the dot product we are basically uh, ignoring the part of the corners, right? Or in the computation, the corner parts is not that much as compared to the center part, right? To resolve that problem, we usually use the padding. Basically, padding does mean that your image had been padded with the padding we had used the padding in CSS, like cascading styles. So what we used to do with the padding, like if we wanted to pad any element with the some of the pixel, will basically declare the padding over. The same thing had been happen over here. The padding does mean that it pad out your whole image with the 000 values. So your uh, the feature set would be rich. As you can see, the same image, uh, uh, the feature set was 3 by 3 in the last case, but right now it's kind of 5 by 5 using the padded image, right? So your output feature set would be rich if you're using the padding. The stride means that how many times, or how many values you are taking at the same time. Like 3 by 3 stride or kernel basically means that your window, or your sliding window is moving, or skipping the three values at at the one time. So right now it's a kind of 3 by 3 stride, where you can see that each and every time, sorry, it is kind of 1 by 1 stride. So each and every time it basically uh, sliding through the one value and moving forward through the one value. If your stride is high, then the movement of sliding window would be faster than what it is right now. Higher stride does mean that your input image is kind of too huge, and what you wanted to do is like you wanted to compress it. You cannot compress it basically because directly via 3 by 3 sliding video you cannot compress it in the lower dimension, but using higher strides you can do that. In the bottom of the screen, as you can see, there is an example of padding and the stride, or like your convolution layer as well, right? So the input shape is 4 into 4, 28, 28, and 3. 4 is like kind of your number of batch, or like how many elements are there. 28 by 28 is the same pixel we had used for the image input, the size of the image input pixel, and 3 is number of channel. So right now we have 4 images, which is 28 by 28 and having RGB colors, right? And what we are doing is like as a X, we are taking that input image and converting or normalizing it into the vector space, right? And then using Keras layer uh, with padding same does mean that we are not adding, we are adding the padding as 0 0 and activation value activation we'll explore in the next slide. Right now, uh, uh, this convolution basically take 28 by 28 image and convert into the lower dimensions, or like set the features over there, right? Okay, that is the part of that feature detector, or like padding and stride. That's how it works. uh, in this example, the major portion is like tf.keras.layers.convolution 2d. Like 2 and 3 are the uh, basic are the basically width and the height of your dimension, or the dimension of the vector they are processing. I'll explain the same thing in next slides, but right now it is kind of we'll calculate, or we'll take one example of this convolution 2D, or why we took 2 and 3 over there rather than 4 or 5, 6 or 7, or any random number, right? And then activation I had defined, padding same, or padding veiling. There are two major values over there. You can go out there and find it out in the documentation how it works. Input shape is basically shape of your input, like what kind of input you are taking. And then as you can see at the end of that function, we had put, or we had called the x as a input, right? So it does mean that x is the input, convolution 2D is the definition of the function, and y is the output basically, right? Okay, let's move next and understand the whole convolution layer, right? So as we had seen, it basically accepts three major type of things, like width, height into the channel, like width, which is 28, height 28 in the last case, and d is 3 basically, which is the input channel, right? uh, it requires basically four hyperparameters. Hyperparameter is basically whatever parameter you are using to create your neural network called hyperparameters, and it kind of dynamic basically. It freezes with the graph, but that isn't a talk of this lecture, so I'll not going to explore it more due to the scope of the lecture basically. So the first part is number of filters, which is k, right? And then there's spatial extent, which is f, then stride s, and amount of zero padding, which is p. K and f is basically what we had defined earlier, right? 2 and 3, right? Number of filters, and spatial extent is like how deeper you wanted to go with that particular image, or that particular dimension, right? That might be a sound, that might sound confusing, but we'll skip it for now. I'll explain it further in details. Then what it does, it took K, F, S, and P as an input and produced volume of W2, H2, and D2, which is the same thing, width, height, and the channel. In this case, channel might not be 1 or 3. It would be the more high dimensional channel, right? So the formula of W2 is equal to W1 minus F, which is spatial extent, into 2p. 2p does mean that whatever padding we are giving had been added into the image, and then divided by stride plus 1. H2 as the same formula. It does mean that width and height will be computed equally by the symmetry while adding the stride and padding, right? And the last part, or D1, is equal, or D2 basically. D2, the output is basically the K. K means the filter. Whatever filter you are defining as the first parameter of your convolution 2D would be output dimension of your convolution layer. Let's take an example. As you can see, the example in the screen on the another side, where input is 227 by 3. 227 height of the image, 227 width of the image, and 3 channel of image, red, blue, and green, RGB basically. So in this case, W is 227, F is 11, which we had given spatial extent, S is 4, which is tried as a 4, padding as a 0, and K as a 96. K means the filter, basically 96. So each time we wanted to, our sliding window will move 96 by 96 uh, vector, basically feature, right? Now, as you can see as an answer, which is 227 minus 11 divided by 4 plus 1 is equal to 55. So 55 is the size of your convolution neural network. The output volume would be 55 into 55 into 96. 96 does mean the K filter we took as a 96. So if we go back to this part, if your image is 227 over here, the feature detector, or like the extracted feature map, would be there is a spelling mistake over there in the last part. Feature detector, it's a feature map. Basically the feature map, your output would be 96, or sorry, 50 by 55 of input size and having 96 dimensions. Okay, let's go further with the same thing. As you can see in the first convolution layer, you can see the 24 by 24 into n1, and you can see the stack of the network, stack of the whole part as the 96. So the kernel 96 does mean that it basically perform 96 filters on your image and converts it into the lower decompose, like it decompose your image with 96 filter and stack it out. So now your data is 50 by into 55 into the 96 dimensions. So x-axis 55, y-axis 55 values, 0 to 55, 0 to 55, and your z value basically is, or your dimension of that vector is 96, right? Okay, so far so clear. Convolution layer, basically it does convert your input image into high dimensional or compressed high dimension data using multiple filters such as sharpen, blur, detect, etc, etc, right? Okay, now let's move ahead. The next part we had seen on, and that architecture was basically pooling, right? So let's take the output of convolution 1 and put it out over here. So it is a 4 by 4, 4 by 4 into 1 vector over here, or matrix, basically, which defines the feature map, which is the output of the convolution 1 network. Now what we are doing over here is like to basically compress data more, or to basically only focus on the value that matters rather than the focus on the value which are not matter, right? So to do that, what we are doing is like on that feature map we are performing the pooling. There are three type of pooling. First is maximum pooling, second is average pooling, and the third is sum pooling. As name suggests, as the sliding window is 4 by 4, and what it does basically in max pooling, it takes the maximum of that 4 element. Average pooling, it took the average of that part. In the sum pooling, it took the summation of that part and converts or pool the data into the still a compressed mode or a better compression mode, and just focusing on the values which is necessary. Because in this case, in the max, generally people used to go with the max pooling, and it is the max pooling and average pooling people used to prefer in a major case. Why they are preferring that, that is the another scope of the whole lecture, and I'm not going to describe it over here. And there are so many resources also available on the internet where you can get the information. So now let's understand the same thing. What it basically does, it downsample your feature map into the non-linear values, or like it applies activation map on it and just focus on the values that matters the most. In max pooling, the first array, as you can see, for by the sixth value is matters the most, because it is the pixel which we are going to go forward with, right? The same thing had been converted into the code as in the bottom of the slide, where you can see the x as the xd 3 by 3 vector, and which had been reshaped or flatten out into the 1 into 3 by 3 uh, 1. The first one does mean that the only one element, 3 by 3 is basically size of vector and converted out into the single channel rather than the 3 channel, right? So there, that is the reshape part over there. And then what we did is we had applied maximum pooling over there, where pool size is 2 by 2, as you can see in the feature map. 2 by 2 array we are sliding with, which is the pool size. Stride is 1 by 1 and padding is valid. You can also perform stride and padding with the max pooling as well. And using the max pool function, we had measured, or we had took the input as the x, and which performs the max pooling on that vector space, right? Okay, moving next, let's figure it out the basic algorithm of the pooling layer. What it does, it actually accepts the volume sizes W1, H1, D1, requires two hyperparameter. Basically, there's a spelling mistake again, which is spatial extent F and the stride S, and produces the volume size of W2, H2, and D2. The formula is the same without the padding. W1 minus F divided by S plus 1. H2 is equal to H1 minus F divided by S1. And D2 is equal to D1, which is the dimension which we had defined in the last pooling layer, or like the dimension of your data is never going to change in the pooling layer, right? It will remain same. Your dimensionality will remain same. That's why it's pooling, basically, because we are just selecting the higher value from them. We are not losing any information, basically, right? While in the convolution, it would change. Okay, moving next, you can also see, as you can see, we had in the first convolution part, we had seen the activation function value over there, right? Let's understand that why we need activation function is in convolution 2D. So what basically activation function did, as there is two example over here, the sigmoid and the ReLU, right? The sigmoid deal with the minus 10 to 10 values, or basically from minus to any input you give, it will give you the probability in between the minus 10 to 10, while the ReLU is will give you the probability in between the 0 to 10, right? So to increase the non-linearity, basically, or the learn higher dimensions from the complex data, we require the activation function. What basically activation function did is, like, it explores, or it converts your, it focuses on the part of the data which is like high dimensional and which is basically more important in the same case. So if we give the input of our vector and the activation function, it, in the case of the ReLU, it converts any of the value into 0 to 10. So we can have better information over there which we wanted to explore, basically, right? So in general case, it basically increase the non-linearity in your data, where you, with the non-linearity, with the, like, if your data having more or higher non-linearity, your algorithm can learn more from it, basically. That is the what, why we are putting the activation function over there. As you can see, the examples of same activation function in the bottom of the slide. For the sigmoid, we had defined the activation at the sigmoid. For the ReLU is the same. So what you have to do is, like, you have to just define the, in the TensorFlow, you have to just define the name of the algorithm as the activation, and everything else TensorFlow will do as the, in the abstract way. You don't have to deal with the background mathematics or execution of the program, right? We took the same input, 4 images, 28 by 20 pixel, with the 3 input, and we had normalized it and then put it into the convolution 2D, right? Okay, that is what activation function does. The next and the uh, the last part of fully connected layer before we are getting the output or sorry, convolution neural network is fully connected layer, or FC, basically, where we are mapping the extracted visual features to the output, or basically the high dimensional data we did got from each and every convolution in the pooling layer. We are converting those data into the probability. That what fully connected layer does, or by mean that it converts your high dimensional data into the single dimension, uh, using which can directly be converted into the output, right? That was fully connected layer do, basically, and that was fully connected layer mean to do. Uh, Okay, let's move further to understand. As you can see in this diagram, there is the same way. There is a convolution layer 4 into 4 into 1. Then there is a pooling of 4 by 4, and then there is another layer of there is a input layer 32 by 32 into 1, and then we are converting it into the 8 filters, right? Or 8, basically using 8 filters, we are converting it into the 32 by 32 into 8 dimensional data, and then using that data we are converting again it into the 8 by 8 convolution features. Now the second convolution, what it does, it basically if we are we are taking facial structure as an input, the first convolution would extract the higher features, or mid-level features, or higher level features, basically the structure of the face. Second convolution would extract the basic or the structure of the ears, or basically eyes or nose or something like that. And if there would be a third convolution, it would basically extract the features such as line and edges, as we had seen in the last lecture, right? So the same thing had been happening over here. Each and every time, with each and every convolution and the pooling layer, we are extracting more details, or we are getting more high dimensional details, or high dimensional data from that particular image, and converting into the vector space. And then after the whole part, we are converting into the 1 by 1 into 256 vector, which is completely a fully connected layer, and then we are connecting it to the output label, which is the possibility of the output. In the binary classification, it would be like the, as we had seen in the last lecture, spam or non-spam, right? Or cat or dog. Or basically in the multi-categorial problem, it would be 0 to 9, right? As you can see over there, there is a function called softmax, right? So what basically softmax does, let's understand that as well in the next part. Okay, basically same diagram repeated over here. So many two convolution layer, one max pooling, and then flatten out, and then there is a last part which is a dense layer, or basically fully connected layer, and there would be a softmax layer, and then there is a output layer. Softmax is basically, it converts your fully connected output, or your logit score, basically into the probabilities. As you can see in the first image, the logit score, or y is 2.0, 1.0, 0.1, and using softmax we are converting into the probability, such as probability of 0.7, 0.2, and 0.1, right? The softmax is basically take the set of values and squeeze them into the values in between 0 to 1, such that the individual outputs sum up to the 1, basically, as we had described over here. For example, in this case, 0.7 plus 0.2 plus 1 does mean the 1. The total outcome is 1. So your probability would not be more than 1. So you can decide, like, is it a cat or dog, or is it a spam or non-spam? So it converts your high dimensional logit scores into the probability in between 0 to 1, right? Now, in the first code part, you can basically use the Keras layer softmax to compute this softmax layer, and you don't have to deal with the mathematics. But with the softmax, what you have to understand is you have to also understand the cross entropy. Cross entropy is basically the lost which we apply on the softmax layer. Like what softmax layer does, it's convert into probability, and then we have to convert that probability into the loss function, right? As we had learned it from in the last lecture. And as you can see, there are two major values, y true and y prediction. Y true is the actual outcome we require, and y prediction is predicted outcome we had predicted from the last layer of softmax, basically, right? And what binary cross entropy does, it measures the distance between the two probability distribution, like the x true first probability distribution, y prediction second probability distribution, and it gives you the distance in between that two part, and we can take that distance as the loss function, basically. Yesterday, one person had asked in the comment box, like, what is the, can you explore more about the binary cross entropy? So this is how binary cross entropy works out. We'll understand it in detail in the next part as well. But before that, let's understand the regularization. Regularization I described in the last lecture as well. It basically, what it does, at the end of, or to basically overcome overfit and the underfit, or in your network problem of overfit underfit, you can use four major concepts to regularize your data. It is like L1, L2, loss, batch normalization, and dropout. Dropout we had learned yesterday. Batch normalization is like kind of, as you can see in the image, it normalizes your data, or basically compress your data, or kind of divide into the limited area. L1 and L2 is like kind of a penalization function, which penalize your weights to focus on the single feature rather than the distribution of the whole probability. L1 and L2 much more complex, and I'm not going to give into the details of it. You can find out any of the material online regarding the same, or this is how regularization works. Why I'm describing this, because it might while we are dealing with the practical approach, you need this part to understand, right? Okay, the last part of the convolution neural network is loss function, basically. We had explained the same part in the last lecture, like how loss function works. And today we are just going to explore the binary cross entropy, which is the loss for the classification problem, right? For example, there is a future X we need to predict. Right? Its labels are red and green. As you can see in the first image, there is a data of X with the two labels majorly, red and green, right? Cross entropy function is described in the second part. I'm not going to give you the details. What it basically does, as we had defined, it basically computes the distance in between the predicted and the actual output using the logarithm, and give you the summation of it, and we can apply it on the as a loss function. Okay, now let's plot out the positive and the negative function as described in the third figure, right? What we did is, like, we had plotted the both of the values differently on the x and y axis, right? Okay, then what binary cross entropy does is basically, if we divide that red and green label into the probability of being green for any given of x, it would give you such kind of line as we had drawn in the first part. Like, more down the line you are, or the less probability it would be red, as it is minus values are red and positive values are green. So the greater the probability, it would be green, and you can easily identify from the graph. Next thing, what we did is, like, we had divided into the sigmoid curve, which basically does what it does. It basically convert your value into the 0 to 1 probability, and you can see the same graph of that x labels, right? Some of the first having the 0.50 probability, the next having 75, and so on and so forth to the 1. The same using sigmoid, we had defined the probability of the red labels using the minus. Why we are using sigmoid? Reason is like we have to deal with the values uh, in the minus as well, right? So if you are using ReLU, you cannot deal with the minus values, or it vanish out the minus value. While in the sigmoid, you can easily identify the you can easily convert the minus values as well. In both you can convert, but when generally you are dealing with the -1 to 1, we usually prefer sigmoid. Now, all together in the last figure, you can see the probability of each and every label over there as the X, right? The first label is like 0.25 percent, right? And then another was greater than that, so on and so forth, right? Now, what binary cross entropy does is basically uh, it gives you the probability of that both part, right? Negative and the positive. As you can see in the last graph, it had given you the if your prediction is 1.0, it means like you have 0.0 loss. If your prediction is 0.2, it does mean you have 0.8 loss. So using binary cross entropy, it basically convert your values into the distance matrix or probability, and then will give you the loss based on the actual outcome, right? And you can penalize that loss to your neural network to make it learn better, right? So that's how binary cross entropy work. I guess this might clear the whole idea behind the binary cross entropy, and whoever had asked the question, it might give you it might have given you the perfect answer, right? Okay, let's move next. This is the basic example of binary cross entropy in TensorFlow, as we had seen explored in the last part. Actual value, predicted value, and differentiation in between. And you can see the output over here as 0.815, which is the differentiation, or which is the loss basically, and to penalize your neural network, right? Okay, so far what we did, we had understood the whole convolution neural network, step by step. Convolution layer, max pooling, and then we understood fully connected layer, how softmax works, how regularization works, dropout, workout, and how actually your loss function binary cross entropy worked out. Next, we'll just take one example of a simple network which is called ResNet 50, right? So over here, this is the architecture of the ResNet 50, which having 26 million parameters. How to calculate these parameters? You can basically uh, measure your fully connected layers, the dimension of your fully connected layer, and you can get the size of the parameter. It does mean that each and parameters of each and every vector space you are processing over there, right? In this network, you can see two major blocks. One is convolution block, another is identity block. And as you can see over there, uh, the convolution block, we are using two convolution layers over there. Like one is moving forward with 1 by 1, 3 by 3, and 1 by 1. Another is directly branching out and then adding into the and skipping the three layers. The same is going with the identity block. This ResNet 50 is kind of very good architecture when you are using the high dimensional image data, and it will give you the very good output as well. What it does, it basically to make sure that each and every high dimensional features go through the whole network. It basically provide a shortcut over there in the convolution and the identity block, where with the convolution 1, convolution 3 by 3, and convolution 1 by 1 again, if it might be possible that you will lose some of the information in between. So to make sure that that information wouldn't be lost, there is a shortcut layer over there which is directly connected to the last layer, and which provides you the consistent information throughout the whole network. And that's why it is very, very informative and a very, very successful network to basically classify the images, right? That is how traditional 50 work. Okay, now it's time to get your hands into the practical approach. So far, we did seen so many TensorFlow image code blocks, right? And we had explored them as well, right? How max pooling layer work, how convolution work. In this example, we're going to classify the basic images, and we'll go through, as we did in the last lecture, we'll go through each and every step, and we'll explore that how it basically works, like how we can, what we had learned so far in this lecture, how we can perform it practically, right? So this is the basic classification problem. What we did in the first part is, like, we had imported TensorFlow and we had imported Keras over there to basically perform vector operation. I had imported NumPy over there, and then to plot that vectors or images, I had used matplotlib, right? So the first thing what we did is, okay, let me execute this. So the importation part would be completed, and then we had imported the MNIST data set, which is like fashion MNIST, right? Which includes this kind of images, which is like 70,000 grayscale images in 10 categories, right? Which is like 28 by 28 pixel images in the grayscale, like 28 by 28 into 1. And it contains so many classes, such as like t-shirts and purses and all those stuffs. The category had been defined over here. There is no execution step. So over here, what we did is, like, we had imported the data set from Keras data set, and we had converted the whole data set, or like divided the whole data set into training image, training labels. Like training image is like 28 by 28 into 1 vector spaces. Training labels are 0 to 9 classes. We need to figure it out. Testing images are like the unseen data, which we use to make sure that our algorithm learn very well. And testing labels is the same labels for the testing images, right? We had downloaded that, and the whole data set had been divided into these classes: 0 to 9, t-shirt, trouser, pullover, dress, coat, sandal, shirt, sneakers, bag, and ankle boots, right? And these are the class name basically, which we need to measure out these labels. Basically, that's why I had declared over here. Okay, let's first explore the data. Like, what kind of data over there? So there is a 60,000 images of 28 by 28. So the training space of training images is 60,000, 28 by 28. Length of training label is 60,000, right? So same thing. We have 60,000 images of in the training part, and we have the same 60,000 labels over there. So the train labels are this kind of things, like an array, basically a vector in a single dimension. Then test images, like we had the whole 70,000 data set, we had divided into the 60,000 as the training images, 10,000 as the testing images, and then 10,000 labels as well, right? So first what we did, we'll pre-process the data. We'll see that we'll convert the images into the range of 0 to 225, 255, sorry, pixels, basically. So as you can see over here, we had converted the whole image into the 0 to 255 pixel values, and you can easily visualize this. This is the input we are giving to our neural network, and we had explored in our first in the last part, where we had explored the architecture of the same thing. It is the input we are going to give to the first convolution neural network, right? The first layer of the neural network, right? Okay, now what we are doing is, like, we are converting the training image and testing image into range of 0 to 1 before processing further. So this is basically 0 to 255. As we had seen that we have to flatten down our images so we can easily give it to the input. So what it does, it basically converts 0 to 20, 225 into the values of 0 to 1, right? And then let's plot the same thing to verify that what we did is right or not. So the same thing, the colorized image had been converted into the black white, 0 and 1 pixel, from 0 to 225. So 0 to 225 RGB, 0 1 black and white, right? So the images had been converted into the black and white. As you can see over here, we took some random samples, and we had visualized the image, and you can see the ankle boot over there, sandals and shirt, t-shirt, trousers, etc., etc., right? Now let's build the model. It is the very simple model using the Keras sequential API. And what we did is, like, we took first layer, a flattened layer, as the input of 28 by 28, and then we took one dense layer of 128, and then we took the last dense layer, as the 10. So 28 to 28 converted into the 128 dimensional space, and then again mapped out, or last fully connected layer is 10, as we wanted to convert it into the 10 category, or we wanted to make sure that it would convert into the 10 basic category, right? So this is how our model is. Let me execute it. Okay, now let's compile the model. There are three major things in the compilation part. The first is loss function, which is the sparse categorical cross entropy. Because we are dealing with the multiple category data, we'll use the sparse categorical cross entropy rather than binary cross entropy, right? Optimizer, which is Adam. We had seen in the last lecture the gradient descent and stochastic gradient descent. This Adam is the more advanced optimizer, or like more advanced gradient descent algorithm, which use the adaptive learning rate. And matrice is like the accuracy we wanted to basically show over there, or we wanted to monitor the accuracy while we are training the model, right? So let me execute this as well. Okay, now in the training part, what we'll do first, we'll feed the training model, and then we'll evaluate the accuracy. So let's first train the model. Over here, model.fit mean like we are training the model using training images as the first argument, training labels as the second argument, and epochs as a 10. Epochs does mean that how many mini batches you wanted to execute, right? So let's do it. So as you can see, with each and every epoch over there, there is a loss loss decreasing, accuracy increasing, as we are measuring out accuracy. And with each and every epoch, we can visualize the decrease in the loss and increase in the accuracy as well, right? Okay, let's complete it, and you can see the higher accuracy with each and every execution of epoch. The data 1875 described over here is like we are taking 1875 samples from it. If you increase this epochs, you will get the more better accuracy over there. I had just defined 10 epochs, as we have limitation of the time over here. So it is giving you the 0.91 accuracy, which does mean that 90%, 91% of accuracy. But how you can check that this is the right accuracy? Because what we did, like we had given the images from the training, and we took the accuracy from the training itself. So we cannot. It is like the teaching a child about something. Until and unless we can see he's doing something, we cannot evaluate it, right? So to do that, what we did, as in the first part, we had divided 10,000 images as the unseen images, which we had not given into the training part. And what we'll do, we'll perform evaluation on it, or we'll test down the model, train model on that images, and we can easily identify how much accurate it is. So as you can see, training accuracy was 91%, but testing accuracy is 88%. So this is how basically we did the evaluation part, and our model is 88% accurate. Now let's make one prediction to check it out using the probability model and the softmax basically. So using the predict API from the test image, I had predicted this, and then by getting the prediction, I put the argument max, which give me the output as the 9, which is the ninth label of that part. And if we convert this test label, it will give you the ninth part. And if you will plot the image of that part, you can easily see uh, the plotting of the image over here, which is like 96% of the ankle boot. And over here, you can see the graph from 0 to 9. Like it is like from the fully connected layer, you are getting the logics where while applying the softmax on it, you will get the probability. And using softmax, you can define the which class this image has been attached to. And with this logics, you can easily identify that it is the more accurate it is the 9. Because we had applied softmax, you can see that the 7 number has the whole probability is 0 to 1. Right? You cannot see the multiple probability over here. Now let's do the another example. The sandal we took over here, and we did the same thing, and you can see the 84% probability of the sandal for this image, right? Sorry, sneaker for this image. Let's plot some several images to check out that our model is working good or not. Let me zoom out. So ankle boot 96% and sandal 100%, shirt 100%. So you can see that using softmax, we can basically convert our logics into the probability, and we can easily identify that what image is it. And finally, let's do a one single plot out, or let's use the train model to make the prediction about the single image basically. Okay, this is the single image we took from our test image set, and then we had predicted single image, and you can see this is the logics you are getting from your model. And then after applying after comparing it to the on the your plotted value or class names, you can see that it is a pullover over there. So this is the vector had been converted into the probability, and you can easily identify it as a second label, which is 0, 1, and 2 pullover, right? So this is how basically we can perform the classification of image using the basic convolution. It is not a convolution neural network. We had not used the convolution part over here. We had just used the basic neural network over here, and we had defined using the dense layers, right? Okay, now we have I think we had understand the major concerns over here, and we had gone through the practical approach. Now let's understand. We have 15 minutes remaining in this lecture. Meanwhile, what I'll do, I'll explain some of the research papers. Like we'll explore some of the research papers, like how to read it and how to get to it, and how to understand it. And in the next lectures, our team would describe the implementation of the TED part. The next 2 or 3 lecture would be the pure implementation part, where you get the insight of implementation of this research papers, right? Okay, so this is the basically problem we wanted to deal with. It is the product search in wild. So what we want to do is, like, we wanted to search the product from images. Like as you can see, this shoes over here, what we wanted to do is, like, we want to label this shoes as like Under Armour men's shoes, right, from the image. And so what we wanted to achieve with this is, like, we wanted to find out the products from wild images. That's why the problem name is product search in wild. Okay, so the first paper we'll explore is the learning similarity matrix with application of face verification. Like it's a binary cross entropy, or sorry, it's a contrastive loss paper uh, uh, written by Jan LeCun, Reda Hetzel, and Sumit Chopra. Will not will not going to explore the whole part, but I'll describe some of the things. As you can read the abstract over here, the define is that we present a method of training similarity metric from the data. This method can be used to recognize and verification of application where number of categories is very large and not known during training, right? So basically, if we wanted to identify this shoes, right, and if we will work out with the simple algorithm classification, it wouldn't work out because we in the Amazon there would be like lots of products, and each and every day the size of product would increase. So what do we need to do? We have to find out the solution which is like scalable, like which will recognize your image without seeing that image in the training part, right? So that's what we are doing right now using this paper. This paper had defined a distance metrics, like which is this contrastive loss function, right? Constant contrastive loss function. What it does, it basically calculate the distance between your two vector space, right? Or if you are connecting two vectors, or if you are training your images using the true neural network, it will give you that how similar it is, right? So that's how contrastive loss function is used out, and you can see the basic architecture over here, which is called the Siemens architecture, right? I'm zooming it in. There is a GWX, which is the first convolution neural network. X1 is the first image we are giving in the input. X2 is the second image we are giving in the input with the another convolution layer network, and both of the networks are sharing some weights, and both of them are aggregated with the one layer, and then we are calculating or we are updating the weights using this loss called contrastive loss function, right? Okay, now moving next. I'm not going to define each and everything because like we have a very less amount of time remaining, and as you can see over here, there is a comparison of two phase with a TNT dataset, and they had performed using Siemens network. They had basically performed the experiments, right? And in this experiment part, you can get the details like what kind of images they had used, how many dimensions are there in the neural network, and what was the feature maps, what was the kernel size over there, what are the connections, and then how it had been connected with the final output, right? So this is basically a simple verification part where they did is like they had calculated the result, right, using this. So this is the accuracy that they got from the testing image is like false except 111 40.6, and the 10% false except was the 11 which is invalidation part. These are the matrices basically which you might not understand right now, but each and every problem having different matrices. As it is the verification problem, it basically work out in the distance matrix, right? So this is how this paper is. I'm not describing in more, or I'm skipping the most of the part because like I'll give you this link in the presentation part, which I'm going to post on our LinkedIn page basically, and you can get the slides from there and you can read out the whole paper, right? Okay, let's move to the next part or next research paper, which is the Siemens neural network for the one-shot classification. It is the same advancement of that Chopra paper or that contrastive loss paper, and as you can see, this is the data set they had used, omni-globe data set, like one shot. What they wanted to do is like they want to compare the two symbols, or both of the symbols are like same or not, right? As you can see over here, what they had wanted to do is like they wanted to do that this both images are same or not, these are different, These are same. These are again different. And using one sort task they wanted to do is like one sort does mean that they want to classify the image using the one sort. So if if we had trained the images using elephants, in the future it needs to give the output on the lions as well, as the similar images of the lions or non-similar images of the lions as well, because we are generalizing it as we wanted to use it in the product search, right? Okay, so let's understand this approach as well. If you go through the whole paper, they had defined the neural network using this, and they had defined another layer called distance layer. So these are the input layers, these are the hidden layers, and then there is a distance layer as well, and which is connected to the output layer, right? Model guidelines they had defined over there how to get the max pooling or how to do the max pool part. They had used the ReLU function, and the whole architecture had been defined over there. Over here is like 105 input image with the one single channel layer, and then converted into the multiple max pooling, convolution max pooling, then another convolution max pooling, and then fully connected using the sigmoid, and also put out L1 Siemens distance over there in the feature vector, and then again connected it with the fully connected sigmoid layer and take the output as one by one. So why sigmoid and one by one output? Because in this part, what we need is like the two images are similar or not. Using the distance metrics, they are figuring out like the distance is similar or not, and based on that, they are differentiating the images and giving the output. You can get the details of learning, how they did the learning over there, how they did the optimization, what was the learning schedule, what was the hyperparameter things, and then how the data samples had been done, so on and so forth. And then they had defined the accuracy over there, the method 30K training, no distortion, affine distortion, and they got the 90% accuracy, and then with 150K training, they got the accuracy of 93.42, right? And they had also defined that how it is good compared to the other methods. Humans had been 95% right, and the hierarchical Bayesian program had been right by 95%, and convolution Siemens network is 92%. Another thing I wanted to explain in this part is like uh, why we cannot use machine learning over here, because this problem cannot be solved with the machine learning. Otherwise, what we have to do is like we have to each and every time we have to define the feature set, which will be handmade, and you cannot do the huge scale products search with the handmade. So that's why we use deep learning over there. And you can basically, if you go through the paper whole part, you can get the reference of another papers from they got the basic thing, right? Okay, now the last part we'll explore the another method to solve the same problem, which is the triplet loss. With the Siemens network, the problem was we cannot basically get the exact output if we are comparing the white wolf and gray wolf, right? Or white bear and gray bear, right? So the model would confuse and define it as the same. Using triplet loss, you can solve this problem. Okay, let's not go through that part. Let's go through the this blog. Basically, this is the basic triplet loss and the mining approach for the same, like how we can do the triplet loss. Let's understand the same part. We have around 5 to 10 minutes last. Let me explain the basic things, how it works. Okay. So what triplet loss basically does, it basically the input had been defined while training part. Input had been divided into three parts, like anchor image, positive image, and negative image. Anchor and positive would be the same image. Negative would become different image from the both of them, and will convert this images into the embeddings, right? Which is like the last feature set we had seen in our convolution neural network. And this whole convolution share the weights with each other, right? So this is the basically basic part. Using this loss, maximum of d, the distance between anchor and p minus distance between anchor and negative plus margin, maximum of 0, and this part would give you the loss function of that distance metering, and using this you can basically uh, differentiate three basic images. This approach had been very useful in the face verification, right? And you cannot do the face verification using the Siemens network, but you can do the face verification using triplet loss, because it differentiates the very uh, high dimensional data, which basically completely similar, while as far as the concern of the feature set, at our each and every person having the kind of similar face structure, right? Nose, eyes, hair, and all those stuffs, but still some of the very high dimensional features are differentiate, and that's how this triplet loss differentiate the whole part. This is the basically the mining part. I'll not explain it right now, because in the next lectures our team is going to give you the insight about the mining of the data. And the last part, what we'll do, will explore the basic higher visualization of the output on the tensor board, right? As you can see, this is the triplet loss had been applied to the MNIST dataset, and you can see in the X, Y, and Z, all three-dimensional, three-dimensional data. We had differentiated each and every images. Like we had made the seven, like each and every figures, like number 1, number 3, number 7, number 0. You can see, and you can see the placing of each and every part, and the uh, two kind of dimensional space which have not higher distance. You can see, you can easily identify the similarity in between. As you can see, 8 and 2 are nearby in the dimensional space, as they are sharing the same features, but it had been clustered into the different dimensions of that particular X, Y, and Z axis, because they having some of the features which are completely differentiate of that part. Some of the figures you can see in the 7 somewhere missing, or the 7 had been included into the cluster of 1, which is the same problem we are getting in each and every time while we are differentiating the in one sort classification. Like sometime due to the similar features, uh, some images get similarity while training. So this is the problem of training or mining part, which can be solved using multiple advanced research papers had been defined and throughout the years, which you can go out and explore in the at the on the internet, and you'll find out so many research paper had been done on triplet loss, Siemens network, on the constructive loss as well. Okay, that's it from my end. I think today we had completed the whole part at the exact moment, and now we'll start the question answer part. And tomorrow the team would take the next lecture, and they'll give you the major insight of the practical approach of the Siemens network and triplet nodes, how to define the data model, how to distribute the data, how to get the data modeling and all those stuffs, and then how to practically go forward with the same part. Okay, I hope that this lecture had been insightful for you. We had learned the convolution neural network and the coding part of that, and then we performed one classification problem, and then if you will explore the TensorFlow beginner tutorials, you'll get the information about the convolution neural networks as well. And then we had read the some of the research paper about contrastive loss and triplet loss as well, and we had visualized the high dimensionality of that data, which we had converted using the triplet loss and neural network basically. Okay, I'm completely done with the part. I'll ask Mr. Narendra to go forward and then conclude on this lecture.
Thank you, sir. Thank you very much for this wonderful session. Now, let us move towards the questions which are asked by the viewers during the session.
Okay.
So, the first question which I have seen, that should feature detector B only matrix, and how should we take the values of feature detector matrix?
Okay, so basically, in the mathematical approach, you can get the information by getting the output of the convolution neural network, but it is not required basically because the libraries such as TensorFlow and PyTorch gives you the very abstraction of the deep neural network, and you don't have to deal with the each and every part. If you go through the internet, you'll get the so many examples of such kind of things, like how to visualize each and every convolution neural network, and you'll get the idea that how it basically works.
Okay. So the second question was, what is the need of optimizer?
So the optimizer is the fundamental or the major thing which updates your weights. As we had learned about the gradient descent yesterday,
Hmm.
GD is the optimizer. Like gradient descent is
Right.
the optimizers. Is the optimizers we need to update our weights based on the loss function. It is the most required field, which is the dynamic. Like it updates your weights based on your loss, or like which we had yesterday. We had visualized the landscape, basically the whole high dimensional landscape, and where we need to go through the local minima in the particular network. So to get the local minima, you require the optimizer. So there are so many optimizers: gradient descent, statistical gradient descent, Adam, RMS prop, and which everyone having their own need, and the based on use can use it.
Yes. The next question was, what basis should we decide the number of convolution layer in the network?
Okay, so it is basically the deciding the convolution neural networks. The parameters of hyperparameter is basically a research field, kind of research field. So as I had described the ResNet at the end of the whole part, there are so many other networks as well, like MobileNet, VGG16, Inception, and the latest papers are like the advanced version of the ResNet as well. So uh, there are so many networks had been already defined. So don't get into the finding the hyperparameters of like or creating a neural network by your own, because it's a completely research field, and you will never get the output, because this networks had been like research, and it took like more than 5 to 6 years to get the one basic network. So what you can do right now is like you can use any of that network, but if you really wanted to get into that part, try out multiple combination. It's a trial and error. So
Right.
neural network is a black box basically, and it's a completely trial. Finding a hyperparameter, it's a completely trial and error part. You try multiple things, and then you get into it, and then you got the hyperparameters. Yeah.
Yeah. So, sir, there is one more question. Can
Mhm.
you give some brief idea of applying neural networks on numeric and categorical data in text dataset?
Okay, which is the NLP basically. NLP having the different format than we used to do with the image data. It basically, with the NLP, you might have to pre-process data, like convert data into the tokens and tokens into the vectors, and then with that vectors you can give it to the neural network. But the input size of the neural network would be dynamic in the most of the cases. If you will go through the multiple research papers such as Bhatt, Robert, GPT-3, GPT-2, the latest research papers, you'll find out that how it works and how neural network had been used in the NLP as well. But in this series, we are not going to cover the NLP or text data
Yeah.
or numerical data. Basically, we are just focusing on the image data, but you can by your own explore the things, and it's if you will really get the insight, if you will really understood this lecture, you can easily identify that there are so many similarity in between the both approach.
Okay. So all the questions are covered, sir. So thank you very much for this informative and detailed session. And I request all the viewers that tomorrow we are having the practical approach session on understanding TensorFlow, and this will be covered by the data science team of Zuzotech Private Limited, Surat. So tomorrow we will connect sharp at 3 o'clock, and we'll have the session on practical approach, right, sir? Sir, would you like to say something to all the viewers? If suppose they want to practice, so what prerequisites
Okay.
should
Okay. So
they
what you can do is like I had gone through the one simple example. You can go out there and you can explore multiple example. You can find it out in the beginner approach of TensorFlow, and you'll find out so many notebooks are there. And just go out there and execute some of them and understand how it works. Basically, in the tomorrow 3 lecture or this next 3 lecture, basically it would be like more or less it would be like very hard or complex programming and
right?
the understanding of the complex formulas and research papers, right? And before that, I would just like to ask you to get your hands into the programming as well and explore major things. And as well as if you did not get the time, just watch these lectures 2 or 3 times, so you'll get the better understanding, and then for the next lecture you'll understand it. Otherwise, you'll not get the how it works. Basically, they will explain the research paper with the very deep fundamentals of mathematics and how it works, and then they'll convert that mathematics into the programming. So that is how the next 3 lectures would work.
Yeah, and I also mention here that all the lectures or the sessions which will be covered during this 6 days STTP. So all the
Yes.
sessions are available on the YouTube RNGPIT YouTube channel. So anyone can go there and access all the lectures anytime. So so here, sir, we are concluding. Thank you very much. Thank you very much, Arjun sir, for today's session, and thank you all the participants for being with us. And we will meet tomorrow at sharp 3 o'clock. Thank you. Thank you very much.
Okay, thank you guys for your time, and I hope you enjoy it. Thank you, Narendra sir, basically to give us the opportunity and give us chance to explain what we basically know and share our knowledge. As well as this would be my last lecture. So
Yeah.
if you have any doubts or anything, you can go on the LinkedIn from the viewers, and you can ask me any question. I'm not assuming that each and every question I'll answer at the same moment, but I'll try to make sure that I'll answer your most of the queries and questions. So have a good day again. Thank you, Narendra sir, for
Thank you.
everything
Thank
you're doing. You're doing very hard work to
you. Yeah.
maintain all those things, and I really appreciate your efforts. And thank you guys for joining us. Have a good day. Bye bye.
Bye bye. Thank you, sir.